Welcome to our lecture on hyperspectral image classification. This week we will discuss about different deep learning techniques for different tasks on hyperspectral image. We have briefly discussed about hyperspectral images in the starting week of this course. However, we would recap a bit about the basics of hyperspectral images, and then we will start discussing about the classification techniques in today's lecture. The hyperspectral images are indeed different from mere RGB or multispectral images. So in this course, we discuss synthetic aperture radar and the hyperspectral images, which needs quite special attention even when designing algorithm or architecture, whereas the otherwise 3-band images or even 4-band or slightly more number of bands multispectral images, they don't need so much of special attention when we try to adopt some architecture from, let's say, computer vision domain. So why so? Because the hyperspectral images capture not just 3, 4 or 10 bands, it captures hundreds of narrow spectral bands. Thus, each pixel contains a detailed spectral signature. This specially enables material identification, which is important in many downstream applications in Earth observation, and thus in Earth observation we are quite interested to use hyperspectral images. Of course, it's not just Earth observation, there are also other domains who uses hyperspectral images. However, Earth observation is one of the primary domain where hyperspectral images are used. To understand a bit more about this difference between the RGB versus multispectral versus hyperspectral, we have to understand that RGB images, we are talking about only 3 bands. The multispectral sensors, on the other hand, still capture a limited number of spectral channels. The hyperspectral sensors capture contiguous spectral bands, which can be in the order of hundreds. And as I already mentioned, that the higher spectral resolution improves material discrimination. So in a way, to understand the difference between the multispectral and hyperspectral images, you can think like this, that if you were, let's say, plotting wavelength in the x-axis, reflectance in the y-axis, you can think of as if, like for the different bands, your plot was like more discrete in the case of the multispectral case, whereas in the case of the hyperspectral, it's as if continuous plot. Thus, the hyperspectral data forms a 3D cube where 2 dimensions represent the spatial information, and on the top of this, the 3rd dimension represents spectral information, and spectral signatures vary across materials, which enable it for material identification, as I have already mentioned. To think a bit about the applications of hyperspectral imaging, it's quite useful in agricultural crop monitoring. If we have to differentiate between different crops, which probably looks quite similar, with RGB images or multispectral images, we can use hyperspectral image, and there most of the time they will show some difference. Very importantly, it's used for mineral study or mineral exploration. So if we had to find, okay, like this particular mineral, a new place where we want to discover this, or let's say like, okay, we already know that this mineral exists in this place, and we want to keep a check on its mining related activity, we can use hyperspectral images for this. Similarly, it's very useful in the military surveillance applications. Again, due to its capability to identify material, this can help in tracking different materials of military interest. Different materials reflect light differently. The spectral signatures act as material fingerprint. Similar classes may have overlapping signature. The classification relies heavily on spectral separability. However, we have to also understand here that the adjacent spectral bands are often highly correlated, and thus, in a way, we have redundant information, which means this will also increase associated computational cost. And thus, in many applications with hyperspectral image as input, dimensionality reduction becomes an important step. Dimensional reduction could be done by either feature selection, like let's say we have a number of bands and we want to select a subset of those bands, or feature extraction, like we, let's say, convert this feature, like let's say 200 dimensional, like in the band space, to a new input vector, let's say 100 dimensional. So we are not selecting subset, rather we are converting them. And this may often improve efficiency. Of course, we don't want to just, like take the RGB bands or like RGB NIR bands out of this. That would not serve our purpose. Then why even work with hyperspectral images? So this is where we need to be, of course, very careful. If we just drop too much of information, then it defeats the purpose of using hyperspectral image. However, due to this redundancy, maybe we don't also want to work with all the bands as it is. As we have already mentioned that high dimensional data, this will usually require more training samples if we are working with learning based approaches. And often we do have, in such cases, very limited level data. If we think about the downstream applications of the hyperspectral images, like we are trying to do fine-grained crop classification or fine-grained material classification, it's often not so straightforward to collect a lot of label data. We cannot really, use on OpenStreetMap or some kind of public annotation to collect data for such applications, and hence it turns out that, okay, we have limited label data, and data on the other hand is high dimensional, so indeed there is a risk of overfitting. And thus, as I have already mentioned in the last slide, that feature selection or extraction can elevate this issue to some extent. The dimensionality reduction reduces spectral redundancy. This may help computational efficiency. This may help reduce overfitting. We can use, let's say, PCA. We can use also, of course, some kind of subset selection mechanism where given these 200 bands, we select, okay, like let's say we want to work with this 100 bands. Before further discussion, so we will come to this dimensional reduction also at some point this week. However, of course, in this lecture, we are more interested in the classification, but we have to understand that many times classification means first there is a dimensionality reduction pre-processing step there. Now, before discussing about classification, one aspect needs clarification. That is, often when we talk about classification in the context of hyperspectral images, this implies pixel-wise classification. That is equivalent to the semantic segmentation, as we know already, right? So this is a bit of, different naming in a different application. So hyperspectral images we will call classification, we will mean something more similar to semantic segmentation. Okay, so with this background, let us quickly start with pre-deep learning based approaches. Here, the traditional methods relied on handcrafted features or directly used the spectral information. They were effective for small data sets and performance was quite limited on complex scenes. K-nearest neighbor has been used in several works, which classifies samples using neighboring labels. K-nearest neighbor is quite simple and intuitive approach, however also sensitive to dimensionality. SVM has been used quite a lot traditionally, and they are also effective with limited label samples. However, as I have already mentioned, effectiveness is limited for complex scenes. Decision tree and random forest, these approaches have also been used. Tree-based methods partition the feature space, and random forests further improve the robustness upon decision trees. Spectral angle mapper is also a popular approach used with the hyperspectral images. This measures angular similarity between the spectra. It's considerably illumination invariant. So in a way, we can think of this as variation of just cosine similarity. So given a reference spectra and given you the target material which you are trying to classify, you will just measure the similarity between the reference spectra and your target. This performs well for material identification, and again, of course, performance is limited on the complex scenes. This sets the stage for CNNs, for hyperspectral images, and with the CNNs, we need to, we of course always pay attention to both spatial and the spectral complexity. However, CNNs in a way, as we have also discussed before, is more focused on the spatial complexity, right? So we need to now think of in a way that it's designed for both spatial and spectral complexity, and thus with this entire background, let us move to more focused discussion on the deep learning based approaches. CNNs, different variations of CNNs, that we'll see how it accounts for the spectral complexity, and at the same time we will also mention about other non-CNN approaches as well, though we'll not go into so much of depth of those approaches. So first architectural variation that we would like to mention is simply 1D CNN. This operates along the spectral dimension only. Thus, it captures spectral complexity. It's quite computationally efficient. It ignores the spatial neighborhood information. So, let us ask ourselves this question that, okay, like what kind of hyperspectral data we would simply use 1D CNN? The answer is that if the resolution, the spatial resolution is probably coarse, so maybe we think that, okay, this particular information, this doesn't benefit so much from the spatial context, rather spectral complexity is what we want to account for. Maybe we just go for 1D CNN. Now, moving ahead to our usual 2D CNN, the version of the CNN that we are habituated to work with. So this uses spatial patches around the pixels. This learns texture and contextual patterns. If we think of only one filter, okay, so most of the time if we think of, like one particular layer in the 2D CNN, of course it has like, let's say 64 filters, 128 filters, depending on the design. But if we think of just only one layer, the output doesn't retain a depth dimension. Whereas we will talk about another version which will retain the depth dimension. This works, the 2D CNN, as we have already talked about, right? 2D CNN with respect to the RGB images, with respect to the multispectral images, 4-channel or 6-channel. So with these reduced spectral channels, 2D CNN works quite well. There is probably no need of like, okay, thinking of another innovation or another variation on the top of this. However, this is not the case for us, right? What we see with the hyperspectral images is that we are working with hundreds of spectral channels. So this motivates us indeed to think beyond this. So 2D CNN, again, like thinking of like, okay, if our input was H cross W cross 200, suppose the kernel size is 3 cross 3, each filter will span actually all the 200 channels. So a single filter will in a way have the shape of 3 cos 3 into 200. Now, before moving to, like the next variation of the CNN, let us briefly discuss about a particular variation of attention called channel attention. So since in the hyperspectral images, we are working with so many channels, and of course, like, so this is so many channels only at the input stage, right? Of course, now if you started working with the 200 bands already, maybe one of the next layers will have even more number of feature maps. So with this context in mind, it is important that if we somehow can, like select or give a kind of weightage to these input channels. So what happens is that the different feature channels capture different semantic information. Not all channels are equally important for a given image, channels or bands. Or if you're thinking in the terms of the feature maps from one of the layer, not all the features are equally important for a given input feature map. However, the standard convolution, this is in a way treating all the channels uniformly after feature extraction. Channel attention adaptively emphasizes informative channels and suppresses the less useful ones. So how does it work? Let's say we are given this input H cross W cross C. So it need not be, like the input image itself. As I said, that this can be like one of the intermediate channels. So H cross W cross C, and we want to emphasize, okay, like which channels, right, are important. So thereby we need somehow the importance of the part channel. So this will be like a C-dimensional vector, right? So that C-dimensional vector is basically this one, which is then multiplied with the input itself to get the final output of H cross W cross C again. So how to get this 1 cross 1 cross C, which can be multiplied? We can convert this from the input H cross W cross C. We can go to the second stage of 1 cross 1 cross C in 2 steps. Okay, so H cross W cross C, 2 1 cross 1 cross C, 2 again 1 cross 1 cross C. So these 2 steps, what are they doing? The first step, we are just interested to, like summarize. Okay, so we want to collapse the spatial dimension. We want to summarize or keep written only the channel dimension, right? And then we want this learnable step of, like importance. So there, as I just mentioned, like we will have from H cross W cross C, we'll have one step which is not really learning based, generally implemented using global average pooling. Okay, so this just using global average pooling, we are not using in learning, and we are now getting from H cross W cross C input to 1 cross 1 cross C. And now on the top of this, what we'll do is we'll have a step which is learning based, okay, which will learn, like which will finally map to this particular weights which we want to now multiply with our inputs. Okay, so here we can have learnable layers. Okay, and we are getting again 1 cross 1 cross C, and then we are multiplying with the input to get this H cross W cross C output, right? Thus, to summarize, the channel attention, the global pooling is aggregating spatial information into a channel-wise descriptor. A lightweight network is learning the importance of each channel. The feature maps are then recalibrated by multiplying each channel with its learned weight. Okay, so we have already seen 1D CNN, we have already seen 2D CNN, and we have seen also like this channel attention, which we are saying that, okay, like if we wanted to, like on the top of this, have some kind of channel importance kind of idea, this channel attention can be used. Now, let us move ahead to another version of the CNN called 3D CNN, which has been used quite extensively in the hyperspectral image analysis domain. This convolves jointly across the spatial and the spectral dimension. So this is very interesting. It's convolving not just across the spatial dimension, it's also convolving across the spectral dimension. And thus it captures rich spectral spatial interactions. The output retains a depth dimension, and this is widely adopted in hyperspectral classification. So think of this again, like if we had input of H cross W cross 200, and then we'll have some kind of kernel like 3 cross 3 cross 3. So it's not just 3 cross 3, it's 3 cross 3 cross 3. So it's like the height, width, and also the spectral dimension. These all are taken into account. quite often what researchers do is they use a kind of combination of the 2D and the 3D model. As we know that the hyperspectral images contain both spatial information as well as rich spectral information, thus a pure 2D CNN would effectively capture spatial pattern, but largely, we can never say that okay, it completely ignores, but it largely ignores the spectral relationship, whereas pure 3D CNN could be computationally expensive, and we would have like with each layer we would have a growing size. We'll see this example. So hybrid architectures, they aim to combine the strength of both approaches, and like hybrid doesn't just mean like you need two hands. You can have multiple hands, but in each hand you can have like 3D as well as 2D convolution. So the 3D, if we are just thinking of like more like a pure 3D CNN branch, so this is extracting more the joint spectral spatial features. The 2D CNN branch learning high level spatial structures. The feature fusion module then will concatenate or add the features from the both branches and then pass on to like some kind of classification layer. So let us see a bit more specific example in this particular context. So let us think about, let's say like we have an input of 25, 25, 30, right? So 30, like okay, 25, 25, you would have guessed already is a spatial dimension. 30 is, let's say, the number of input bands. So it could of course be not just input bands, it could be like, like you had input bands and then you applied some kind of feature reduction on the top of this. Maybe you selected a subset, or maybe you applied PCA, and you now have 30 bands. Now you are, let's say, applying a con 3D, okay, 7 cross 7 cross 7, and let's say you are applying 6 of such filters, okay. So what we'll obtain from here is an output where the 25 is becoming 19, so we have 19, 19, okay. The 30 is becoming 24, okay. So 19, 19, 24, 6. Why? Because we have these 6 filters. So what we see, as I already mentioned, that with the use of this con 3D, we will have, like the feature size will start growing. So that's what is happening. Like we are having one more dimension right here. So 19, 19, then 24, then again 6, right? Which with the use of the con 2D, we would have one less dimension. So now let's say we reshape this and we get, so reshape basically along this 24, 6 along this. So what we get is 19, 19, 144 dimension input, which is now processed with a 2-dimensional convolution, 3 cross 3 and 80 filters, and we get an output 17, 17, 80. Okay, so let us keep this one particular branch. At the same time, what we could do is we could have another branch where what we are doing again, we are starting. So the previous branch is here to the left, and to the right we have this new branch. We are again starting with this 25, 25, 30, 1, and we are here applying now not just one layer of con 3D, rather successive layers of con 3D. Okay, so con 3D once, con 3D again, con 3D again. Okay, and at some time we reshape and we apply con 2D. Okay, and we again get a 17, 17, 80, and now these two we can fuse or concatenate and then process to like some classification layers. So with this we saw a hybrid 2D 3D model. We will take forward our discussion in the next lecture. We'll stop here. Thank you.